So we want to look at what we can see about a matrix without doing the whole calculator business and performing row operations. So in this first matrix that I forgot to record, we saw that the columns of A were linearly independent because there's only two columns, and the second column is not a multiple of the first column. Since we can see that the columns are linearly independent, we know that there will be a pivot in each column of the matrix. So it was really easy to pull out the reduced row echelon form. In B, we have more than two columns. We can't say that the columns of B are linearly independent because there's more than two. We can't just use that one's not a multiple of the other trick, because none of these columns is a multiple of the others. But one of these columns is a linear combination of the others. So without doing calculations, what is the first column of the reduced row echelon form going to be? 1, 0. We know that we have a pivot in the first row, first column, because I can do 2 times the first row plus the second row, and that will zero out the rest of the column. What's the second column of the reduced row echelon form going to look like? 0, 1. We knew that this was going to happen because the second column is not a multiple of the first column. We saw that the second column is not a multiple of the first column, so we knew that the second column must have a pivot in it. Now the third column, is that going to be a pivot column? No, we're all out of pivots. I got a pivot in every row. I could not possibly have a pivot in this third column. I could only have 2 because there's only 2 rows. So the third column, we're going to have to do a little bit of work for, but I tried to make it easy. What's the third column going to look like? Can anybody see it without making any calculations? It's like one of those trivia games that you see at bars. I don't know if they have them anymore. I haven't been to a bar for a very, very long time. But like they put up the thing and then there's four answers. And then it starts off at 1,000 points and it starts decreasing as they start removing answers until the last answer is left and it's worth 0 points. It is 1, 1. The last column will be 1, 1, not a pivot column. And why is the last column going to be 1, 1? Now, it's the sum of the first two. It's 1 of the first column plus the second column. It's 1 times the first column plus 1 times the second column. So there's a lot of times we can figure out a lot of things by looking at the columns. So to recap, we knew that the first column had to be 1, 0 because we knew we can pivot there. That was an obvious pivot. Well, let's recap all the thinking that went into this before we just grabbed our calculator to automatically reduce row echelon form something so simple. There's a pivot in the first row, first column, so that column is 1, 0. Yikes, a little trouble writing today. That column will be 1, 0 in the reduced row echelon form. That's the first thing we noticed. Next, we moved on to the next column, and we saw that the second column was not a multiple of the first column. Second column is not a multiple of the first column. Therefore, second column also pivot column. Therefore, it'll look like 0, 1 in the reduced row echelon form. And then finally, the third column we see is a sum of the first two columns. That's why we can read that column. We can figure out that that column is going to be 1, 1. So the columns in the reduced echelon form have the same relationship as the initial columns in spite of possible row switching. That is correct. Because when we switch rows, we don't change any of the equations that are associated. We can add equations together and that doesn't change anything. If we start switching the columns, now we're breaking rules. Now we're taking the coefficients of x and making them the coefficients of y, and that's not good. But the columns maintain the same relationship as in the initial matrix. That's why the reduced echelon form is so useful for finding these relationships. Any questions? There's one more. We're going to write down a matrix and we're going to see what we can see about it. This is the matrix C. It's going to start off the same way, 1, -2. And then you could probably guess what's going to happen now. The second column is going to be, let's use -3. And someone tell me what I'm going to write next. What am I going to write as the second entry in the second column? Yep, that is correct. I'm going to write a 6. And then the third column is going to be -2, -1 because lazy. What's the reduced echelon form of C going to look like? What's the first column of the reduced echelon form? 1, 0. What's the second column of the reduced echelon form going to look like? -3, 0. And then the third column, that's correct. There's no pivot in the second column. We'll talk about why in a second. And what's the third column of the reduced echelon form going to look like? 0, 1. Awesome. So we see that there's going to be a pivot here, but when we perform that operation, when we do 2 times the first row plus the second row, that zeroes out this 2, and it also zeroes out the 6. This is going to be 2 times this, -3 will be -6, plus 6 will be 0. So we're not going to get a pivot in the second column. We knew that that was going to happen because the second column is clearly just -3 times the first column. And here's the reduced echelon form telling us that information. This second column is just -3 times the first column because I did not get a pivot here. But the third column is not a combination of the previous two. So that's where we're going to get our third pivot. Any questions? If there was an equation, Cx equals b, then x2 would be a free variable. That is correct. First column, pivot column. The next thing that we noticed is that the second column is -3 times the first column. That's what we observe, and so that tells us what the second column should look like. And then the third column is not a combination of the other two because the third column is not a multiple of either one of them. So if there's no way I can add these together. If I add 1, -2 and -3, 6, any linear combinations of these will just come out to multiples of 1, -2. Since -2, -1 is not a multiple of 1, -2, the third column must be a pivot column. Any linear combination of the first two columns will just be a multiple of the first column, 1, -2. So since the third column is not a multiple of 1, -2, it's not a combination of the previous two columns, therefore it must be a pivot column. Any questions? One of the things that I don't know if I've reminded you or not, in every math class, the entire point of the math class is to learn the math so well that you don't have to do the math anymore. You want to get to the point where you don't have to do FOIL, where you don't have to do the factoring process. Make your conclusions without asking a computer to find the reduced row echelon form. Use your human brain to look for those things, because the computer will just carry out and execute what you tell it to do. Any questions? So this was an example of AX equals B. If I do an equation, if I look at this matrix A, the matrix AX equals B, the equation AX equals B, what can you tell me about the equation AX equals B with A, this 3x2 matrix? Is AX equal B consistent for all B in R3? No, why not? Why is AX equal B with this 3x2 matrix? Why is AX equal B not consistent for all B in R3? What do we need for the matrix AX equal B to be consistent for all B in R3? We don't have a pivot in each row. It's possible that there's a pivot in the rightmost column because A does not have a pivot in each row. If AX equals B is going to be consistent for all B in R3, then A needs a pivot in each row, and it does not have that. So the pivots tell us all the things. We wouldn't want to say that there's no pivot in each row, because here's a row with a pivot. A doesn't have a pivot in each row. It's weird. English is very terrible at expressing this. We also wouldn't want to invoke the rightmost column without first invoking an augmented matrix. So the augmented matrix A, B might have a pivot in the rightmost column, because we can see that A has a pivot in the rightmost column, but that's not what we're basing this conclusion on. Any questions? We're just taking this matrix A, we're trying to read the coefficient matrix and think about what it would look like. Any questions? So let's break that matrix out and draw some conclusions on things that are related to A. So let's look at the matrix A. Here's the matrix A again. 1, -2, 3, and -2, -1, 2. And it's reduced row echelon form, 1, 0, 0, 0, 1, 0. So we can see these pivots. We notice that the columns of A are linearly independent. So if AX equals B is consistent, then the solution will be unique because the solution set will have no free variables. So here are the things that we notice. We notice that the columns of A are linearly independent. Because there's a pivot in each column. Since there's a pivot in each column. We know that since the columns of A are linearly independent, if AX equals B is consistent, if AX equals B is consistent, then the solutions are unique. Since A has a pivot in each column, there won't be no free variables in the solution set. But we also know that AX equals B is not consistent for all B in R3 because A does not have a pivot in each row. AX equals B is not consistent for all B in R3 since A does not have a pivot in each row. So this is what we conclude looking at this matrix A. We weren't solving for any specific B. We're just thinking about the kind of B's that make this a consistent system, or a consistent equation or an inconsistent equation, the AX equals B. We're just thinking about what could happen. Very important to know what could happen. Any questions? Then we just have to be careful about how we say it, because we can't just take the phrase not consistent and replace it with inconsistent, because then now we're wrong. So we could say AX equals B is not consistent for all B in R3 because A does not have a pivot in each row. But if AX equals B is consistent, then the solution will be unique because there's not going to be any free variables, no room for free variables in our coefficient matrix. Any questions? Comments? Schneid remarks? So if we wanted to solve and B was 2, 1, 0, then we could look at so we could say, what about B equals 2, 1, 0. So this is just one example. And we would say something like, is AX equal B consistent? Is AX equal B consistent? Because there's a possibility that it's not. Also, we could be asking, is a similar question, is B in the span of the columns of A? Is B a linear combination of the columns of A? That's just the same question. And to do that, we would set up an augmented matrix with the columns of A, 1, -2, 3, -2, -1, 2, and then we put B on the third column. Now we're looking at an augmented matrix, and we want to know if there's a pivot in the rightmost column of the augmented matrix. So to do that, we'll put our augmented matrix in our calculating machine. And look at the first row is 1, -2, 2, close the row, open the next row, -2, comma, -1, comma, 1, close the second row, open the third row, 3, comma, 2, comma, 0, close the third row, close the matrix, close the command, and hit enter. So the reduced echelon form of this augmented matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is an augmented matrix, because I put B at the end of it. So the augmented matrix has a reduced echelon form 1, 0, 0, 0, 1, 0, 0, 0, 1. So in this case, we see that there is a pivot in the rightmost column of the augmented matrix. So the equation AX equals B for this particular choice of B, that equation is inconsistent. B is not a linear combination of the columns of A. Oh, I'm thereforeing too early. The augmented matrix A, B has a pivot in the rightmost column. Therefore, the equation AX equals B, this is for this particular choice of B. Therefore, the equation AX equals B is inconsistent. Therefore, B is not a linear combination of the columns of A. Any questions? All right. So there are other choices of B where we would get a consistent equation. And there are choices of B that would be linear combinations of the columns of A. But all these things, for this particular choice of B, 2, 1, 0, we found that that B was not a linear combination of the columns of A. For that B, AX equals B is inconsistent. For those of you reading ahead into linear transformations, B is not in the range of T. If T maps R2 to R3 is given by T of X equals AX, then B is not in the range of T. This B is not in the range of T. Some B are in the range of T. Some B are linear combinations of the columns of A. For some B, the equation AX equals B is consistent. Any questions? Like I said, it only seems like a lot to remember because it is a lot to remember. You have to remember all of it all the time in perfect detail. You have to state what you're concluding in clear sentences in a language that is extraordinarily picky. Not English. English is terrible. But math is an extraordinarily picky language. All right, let's pause the recording here and let that sit for a second.